So can everybody hear me okay with and without?
With is better.
It's better with? Okay. All right. So my talk today is about the fact that, in my opinion, a wavefolder is not really a wavefolder. And at least not in the way that you would think it is. So I don't know if everybody's familiar with wavefolders, but the very first time that I came into contact with a wavefolder was back in the day when I saw this YouTube video by Befaco. So this is a YouTube video from for the Befaco chopping kinky, and on what kind of intrigued me about this video was that it showed oscilloscope pictures, of the input and also of the output. And so you can see this is the input, the sine wave. And then here in the output, it looks as if this wave is being folded over, hence the name wavefolder. And so if we look a bit closer at this, here I plotted this out. The green signal is an input sine wave, and then the sine signal is a wavefolded version of that same wavefolder. So my thought process at the time was like, look, these bends here, there must be some kind of gain thing going on where this gain is being flipped around, and as a result, this wave shape is being flipped around too. However, so going from positive gain to negative gain. However, I'm going to tell you today that this is not true, and I'll show you why. So before we continue, maybe let me introduce myself for those of you who don't know me. My name is Tom Verschoten. I run 3-tom modular synthesizers. And as a background, I'm a multidisciplinary engineer. So my background is somewhere between electronics engineering, optical engineering, and making mechanical systems in which the other two are housed. So as a day job, I'm an R&D engineer and a maker. And maybe it's worth mentioning that despite having a little bit of musical education, I'm still very much of an engineer. So I'm very happy that I have musician customers who are way better at that portion than I am, as you will see later today. So 3-tom modular synthesizers is my hobby that got out of hand, and I've been running it since 2020. And I'm focusing on boutique analog modules. And I'm based in Bonheide in Belgium, so that's right in the middle between Brussels and Antwerp. And so, yeah, I consciously run 3-tom modular as a side business. So I don't want to make it my main gig so that my income does not depend on it, so I have maximum creative freedom. And then finally, I also would like to mention that even though I'm a very small business, I have very strong emphasis on quality control and traceability, which is evidenced by the virtually non-existent number of modules that came back. So currently I have 2 products out in the market. The first one is Steve's MS-22, which is a very elaborate MS-20 inspired filter that fits in only 4 HP. It's one of the most feature-rich filters in this small of a form factor available in the Eurorack space. Then there is Doppio, my stereo soft limiter and drive. And then there is still Mixing Flask, which is coming in August. If you want to see that, you should come by my booth. Then finally, it's worth mentioning that Steve's MS-22 at some point was #1 in the Modular Grid Top 100, and currently it's still somewhere in the top 10. And there's over 1,000 units sold, by the way. I also offer my modules as DIY kits. And to support DIY communities and engineering, I also offer these wiretap adapters, which facilitate easy connection of your Eurorack to either an oscilloscope or other test equipment. Currently, I have a few retailers out in the world. We have, for the assembled module, Signal Sounds, Perfect Circuit in the US. And then soon Schneidersladen will also be joining that list. And for my DIY kits, you can get my stuff from Tonk and Exploding Shit. And finally, if you'd like to shop direct, there's also my very own web shop, www.treatom.com. So, to get back to the matter at hand, I want to give you some context for what I will be talking about today, or where this discussion is situated in my context. So typically, when you're engineering modules, you'll have a product design cycle, and it starts with an idea, then you go to a functional prototype, and then you go to a product prototype. Now, what I will be talking about today is this here, the functional prototype. And typically, most people, most of my colleagues, will be using breadboards to go through that phase. Now, if you're unfamiliar with that, this is what that looks like. So I stole these pictures from the Joranalog Instagram. Here on the left, you see the Belgian breadboard beast himself. So if you're unfamiliar with these things, so breadboards are these white plastic-looking thingies, and inside they have rows that are interconnected and columns that are interconnected. And if you plug components in the right way, you can form temporary circuits. And like that, you can explore ideas that you have and figure out if they will work in reality. Now, when I look at these pictures where Jordan is doing this, I have a double feeling. On one hand, I'm always super impressed because he keeps track of all these signals going around in that breadboard there, and it works. But on the other hand, I'm getting stressed by proxy because you have to keep track of that, which is kind of ironic being in the Eurorack context. So there's a few pros and cons, as with everything with breadboarding. One of the big advantages is that it gives you instant truth. So you know, either it works or either it burns. Even if it burns, that's useful information. And you don't need to solder, and you don't need to have a PCB made. Both of those are definite advantages. Now, there are also significant disadvantages to this approach, and that is that the connections aren't always reliable. Finding a bug can literally be like finding a needle in a haystack. You need to stock a ton of components. You need test equipment, which can be expensive. And keeping track of changes you make is a pain. Well, at least to me it is, because I'm a scatterbrained person, and I get lost in these things, and then the next morning I come to the conclusion that I forgot to take notes and I don't know what I was doing anymore. So I'm going to show you an alternative way of approaching this problem. I'll show you my way. And using that way, I'm going to explain why a wavefolder is not a wavefolder. And the way I go through this problem, or this part of the process, is using an analog circuit simulator called LT-Spice. LT-Spice looks like this. So on the right-hand side, you have a window where you can draw a schematic of the circuit you want to investigate. And then on the left side, you can plot all kinds of signals that run around in that circuit. Same as with breadboard, these kind of simulations have their advantages and disadvantages as well. So the big advantage is it's free, doesn't cost you anything. You can work anywhere. You don't need to solder either. You don't need PCBs either. You're not limited by test equipment, so you don't need to own any of that. This is a big one for me. Simulation is documentation. So when you simulate it, you save it, it's documented, and the next day the file remembers for you what you were doing. And then it's also very easy to investigate how changes in certain components will affect the function of the circuit. Whereas with the breadboard, you will have to physically plug and unplug components. With LT-Spice, it will automatically sweep through all kinds of combinations. Now, there's also a few significant disadvantages, and that's you can't always find the right models for every kind of component, which is a pain. It focuses on analog circuits, so if you want to simulate something that combines with strongly digital parts, that's tricky. Can be very tricky. There is no smoke. Yeah, you would think this is an advantage, but it isn't. You can perfectly simulate something. The simulation will tell you it's drawing 100 amps, but if you don't investigate and don't look at that, you think everything is fine, and then you build it and it smokes. So be aware, there's no smoke in simulations, but that doesn't mean that it can't smoke if you build it. And then, yeah, the user interface is medieval. It uses function keys, F3 up until F12. It's a pain to get through that first learning curve. Okay, so now I've given you a bit of a context who I am, where this story is coming from, and now we're going to dive into why a wavefolder is not a wavefolder. So back to the chopping kinky. This is the part of the schematic of the chopping kinky. Now, if you're unfamiliar with electronic schematics, don't worry. That's not a prerequisite for this talk. I'm going to walk you through what we're seeing here. So on the left-hand side, we have a VCA that's modulating the input amplitude. And on the right-hand side, you have an amplifier and a buffer. And then in the middle, you have a string of 4 slightly different wavefolding circuits. So that's this section. And then the most simple one of these is the third one, this one specifically. So for this talk, we're going to look at the third one and then try and understand how that works pragmatically by simulating this in LT-Spice. So here I drew up the schematic of this wavefolder in LT-Spice. And on the right-hand side, I did the same thing. I made a little change, which turns it into a simple inverting amplifier. And that change is cutting that wire and then connecting that input to the ground. So the reason I'm showing you this is to kind of give you already an idea that this circuit is closely related to an inverting amplifier. Keep that in mind. So when we simulate the inverting amplifier, you will see that the input and the output are exact copies, except they're multiplied by -1, hence the name inverting amplifier. And then if we reconnect that thing there, that wire, so that it becomes a wavefolder, then this happens. And so you see, I've plotted one extra signal, and that's this signal here at this node that we reconnected. That's the voltage over the diode in this circuit. And if you peer long enough at these signals, you can actually deduce that this is the formula that defines the output. So the output is that inverted buffer plus 2 times that red signal. Is everybody seeing that? Is everybody still following along? Okay. So if we look at this equation, This is the inverting buffer. And then the other portion, and it's summed with a nonlinear saturating function. So an overdrive, if you will. And because this is a sum, we can I can actually say that there's no gain control at work, because if there were gain control, the formula would say output is something times input. And that's why a wavefolder is not really a wavefolder. It is a sum of a nonlinear function, and that conveniently makes it look as if the wave is being folded. Mindfuck. So for the sake of completeness, some caveats, because I'm going to be putting this on YouTube and I want to get ahead of the people who are going to start nitpicking. Probably you can rework that function into something that says V output is V input times something. I started working that out mathematically, and I can tell you it gets complicated real fast. So I'm pretty sure you can work that out. However, that is going to get so complicated that it won't really lead to any useful quick insights, as opposed to my way of looking at this problem, which is a simple equation combined with a plot. So all the footnotes are covered with this, and we can move on. So now we have a basic understanding of how a wavefolder works. Let's now see what other steps we can take to bring this to the next level and then start designing products with it. So I'm going to, in the rest of this talk, I'm going to show you how I now take this and start designing a product with a wavefolder. So I typically work with building blocks. So that means something that's easy to use in many products. And for that reason, a well-designed building block means that it is well known. So I want to fully optimize that building block before moving on and then doing a whole kind of Lego thing where I start making all kinds of combinations and exploring the interesting ones. So well-known optimum behavior, what does that mean? So there's a few things that I typically look at, and that's how will this behave at the edges of the audio spectrum? 20 hertz, 20 kilohertz. How will the amplitude evolve as the frequency gets higher or lower? How will the phase evolve? How much current will it draw? So looking for that virtual smoke, that's also something that I will do. And in this case, I'm also going to look at what's the spectral content of such a wavefolded waveform. So, and in this example, we're going to explore together how the value of that resistor affects things. So we're going to look at the behavior of the wavefolder for 3 different values, 1K, 10K, and 100K. So this is a simulation at 20 hertz. LT-Spice sweeps these different values for me, and it plots each response in a different color. And you can see there's minor differences. So there's a bit of differences in amplitude, but there's no deal breakers here. All of these could be acceptable. So we move on. Then in this plot, still at 20 hertz, I'm also plotting the input. And I want you to notice something that's very important. This yellow line is the input, and this blue line are the different possible outputs. And you'll see that these are here perfectly aligned. So that means they're perfectly in phase. That's going to change if we go to 20 kilohertz. At 20 kilohertz, you see bigger differences. So the 100K has a lot of delay, and so phase is frequency dependent delay. And the other 2 are still kind of looking okay there. So my suspicion at this point is that 100K will not be usable. And this is confirmed if we do frequency analysis, and we can see, so we're plotting the attenuation. Those are the solid lines. So the goes from zero millidecibels to minus 200 millidecibels. So that's kind of a negligible difference. It looks big on the plot, but it really isn't. But the phase is actually, there the differences are more, yeah, they're bigger. And you'll see that for 100K, there's about 6 degrees of phase at 20 kilohertz. Now, this is not dramatic, but if you're going to start combining multiple of these blocks, let's say you build a 10-stage wavefolder, those together will get 60 degrees of phase, and that starts to become problematic. And so this is yet another confirmation that this 100K is probably not going to work for us. Then current draw. So I've plotted the current running through this resistor, and you see that for 1K, the current draw goes up to almost 4.5 milliamps. That in itself, not that problematic yet, but yet again, if you put 10 of them there, the 45 milliamps starts to become problematic, if only for this single resistor, and because there's still other currents running in the system as well. And then we do an FFT analysis of the output wave shapes, and there you can see, and this is kind of interesting, that mainly odd harmonics are coming out. There's no even harmonics, only odd harmonics. And the different values, they all yield odd harmonics. They're a little bit of different mixes, but they functionally, this could be usable, all three of them. So in summary, all values give us odd harmonics, which is good. But then the 1K resistor gives good phase but bad current consumption. The 100K gives bad phase but okay current consumption, and the 10K is the reasonable compromise. So at this point, let's say we have a well-designed, robust building block to play with. And then at that point, you can start exploring product IDs. And now we get to the good stuff, because I know this was a bit dry up until now. So because LT-Spice can also read and write wave files. So I've created a modulated sine wave as an input. I simulate that, and then I write that to a wave file. And that sounds like this. Okay, that's still pretty basic, but what's kind of nice about this and unexpected is this wave file you can then also put in software like Isotope RX, and you can start looking at the spectral content in an harmonic context. And then you'll see that on top of the A2 fundamental, you'll have an E4 that arises, which is caused by the third harmonic and is actually a fifth, 1 octave higher than the fundamental. And then the fifth harmonic leads to a major third 2 octaves higher above the fundamental. So this is really interesting. This is not something that I could have, guessed when I started this exercise. Of course, this was still pretty boring because it's just a sine wave going in with a simple modulation, but you can also put in real actual recordings. So I asked my friend Dries Gussens to record a loop for me, which sounds like this. This is a low pass gate, sine wave going through a low pass gate, I think. And so I have put on there a little bit of amplitude modulation, and then I made one big simulation of many of these wavefolders in series. And we can listen to the individual notes. So here's the input again. this is a one-stage wavefolder. A two-stage wavefolder. I'll jump right ahead to the 8-stage wavefolder. So I also found in this exercise that if you, instead of branching off from the output of these wavefolders, if you then branch off of this diode node of the second stage, you get saturation over that, that first wavefolder, and that is quite pleasing as well. So we can also listen to that. Because when you run a simulation like this, you get all of these waveforms at the same time. So you just define upfront everything you need to record, and then it starts crunching and you can listen to everything afterwards. So this is a mix of folding and distortion. It mainly has a positive effect for the low order wavefolders. For the 8-stage wavefolder, it makes little to no difference. You can hear this. It's virtually identical to the other 8-stage. So at this point, the true engineering is done. And the decisions you make from this point are more personal taste and product strategy. So here it's all subjective. And so I'm happy that I could take you up until this point. Do tell me which sound you preferred later. But before I go to the end of my talk, and thank you, by the way, for bearing with me all this time, I want you to remember two things when you go home. First of all, LT-Spice is quite useful as a tool for designing synthesizer circuits, and I hope I've inspired you by showing you the tip of the iceberg of what is possible. And then finally, I want you to remember a wavefolder is not a wavefolder, or at least I think so. Thank you.